So we have another example we're going to work on here, and we're going to find our critical numbers. And as we said, those critical numbers, we need those to determine max and min and absolute extrema. Okay? The critical numbers we know occur at undefined values, endpoints of the domain, and where the derivative is equal to 0. So we're going to be looking at all three of those things to list our critical numbers. So the first thing, what does this graph even look like? And you guys have a graphing calculator. So if you were to graph it on your graphing calculator, you'd get the top half of a circle with these endpoints at 0, 0, and 2, 0. Okay, so our domain, and again, we can find the domain algebraically. The domain of a square root function is going to occur at whatever that argument, our radicand, under the radical, our radicand has to be greater than or equal to 0. So, for a domain, if we were doing it by hand without just looking at the picture, I would say, well, 2x minus x squared has to be greater than or equal to 0. So this is a polynomial inequality, and we've got to think about where the graph of this is above or touching the x-axis. I can factor out an x, and that gives me 2 minus x greater than or equal to 0. So what we're looking at is a parabola opening down that crosses the x-axis at these zeros, 0 and 2. Okay? And where is the graph? Because I said this was greater than or equal to 0, where is the graph positive? It's above the x-axis between 0 and 2. So algebraically, I can determine that my domain is from 0 to 2. And also, I can determine my domain looking at the picture because the graph only exists between 0 and 2. So any value outside less than 0 or greater than 2 is going to be outside of the domain, and those would be undefined values. So my endpoints of the domain are 0 and 2. So we also need to find the derivative, and we need to find where it's equal to 0. So domain is what I did first. So my second step here is going to be the derivative. I'm going to scroll down a little. We're going to find g prime of x. I'm not going to write that yet. I'm going to rewrite my function. So g of x, and I'm going to take that square root and write it as a 1/2 power. So g prime of x, I'll use my chain rule. That is 1/2 2x minus x squared. 1/2 take away 1 is the negative 1/2 power. And then we say times the derivative of the inside, and the derivative of the inside here is 2 minus 2x. So all of this represents my derivative. And I can clean that derivative notation up a little bit. G prime of x equals 2 minus 2x over 2, and that 1/2, the negative 1/2 can go to the denominator, so I've got 2x minus x squared, and all of that is going to be under a square root. All right, so this stayed up in the top. This piece came to the bottom. And just because I prefer, we can clean this up a little bit. I can factor a 2 out of the top and a 2 out of the bottom, and those will cancel. So I've got 1 minus x over the square root of 2x minus x squared. So we found our derivative, and we need to see where our derivative is equal to 0 and where the derivative is undefined. Okay? So setting this equal to 0, this is my third step, g prime of x equal to 0, I have 1 minus x over the square root of 2 minus x squared equal to 0. And if I treated it like a proportion and cross-multiplied, that denominator would go away, and I'd end up with just 1 minus x equals 0. And solving that, we're going to get x equals 1. So that is a critical number. And then the last piece we need to consider here is the derivative undefined? So are there any undefined values for my derivative? And the derivative here has the same denominator as we were dealing with up above, right? That same expression we originally had to find the domain of. So essentially we would just know that those numbers that would make this 0 have to be eliminated from the domain of the derivative. So we also know that x cannot equal 0 and 2. All right, so we've done a lot of work. We have to consider all of these things. In this problem, there was a good bit of overlap because we got 0 and 2 twice, and they meant different things. But essentially, we found 3 numbers. The endpoints of my domain, 0 and 2, where the derivative was equal to 0. I did that skip. So where the derivative was equal to 0 to x equal 1, and where the derivative was undefined. Okay, so we're always looking at all of those pieces. And in this case, we have x equals 0, 1, and 2 represent critical numbers. So we have one last example in here. We're going to find the absolute extreme values on this for this continuous function. And absolute extreme values of any continuous function, as long as it is on a finite closed interval, we can determine those because we'll find all of the critical points. We've seen 2 examples now of finding critical points. And then the main thing we have to remember is we are going to evaluate the function, not the derivative. We're going to evaluate the function at both the critical points and the endpoints. The largest will be my absolute max, and the smallest will be my absolute min. So we're going to find the absolute maximum and absolute minimum values for the function on the given interval. So the first thing we have to consider are the endpoints of the domain. I have 2 endpoints, right? The regular domain of sine, a sine graph goes up and down repeatedly forever. It's a harmonic function. But in this situation, we have a closed, a finite domain with 2 endpoints. So the endpoints of the domain. We also say, well, where is sine theta undefined? And it's never undefined. The domain of sine theta is all real numbers, right? So our domain is from negative infinity to positive infinity. There are no undefined values here. And then the next piece would be, what is the derivative? And does the derivative have any undefined values or zeros? So my derivative of sine, f prime of theta, the derivative of sine is cosine theta. Does cosine theta have any undefined values? And again, it's just like sine, it has a domain of all real numbers. But then we would ask ourselves, well, where is cosine theta equal to 0? And cosine theta is equal to 0 at a lot of values. Cosine theta is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, infinitely, right? And even in the negative direction, negative pi over 2, negative 3 pi over 2. So in that situation, if we were solving that, we would say, well, that's theta is equal to 0 at pi over 2 plus any pi k. So adding pi, adding half of that unit circle would take us somewhere else. Remember, your unit circle cosine is equal to 0 at the top and the bottom. Pi over 2, 90 degrees, and 3 pi over 2, which is 270 degrees. Okay? So there are infinite values, but we only care about the values that exist between negative pi over 2 and 5 pi over 6, because that's our given domain. So I've written this in a way that illustrates the infinite places where my cosine graph touches 0, but we are only interested in the two spots between negative pi over 2 and 5 pi over 6 where it may touch 0. And so on our given domain, what we'll say is my theta values are negative pi over 2 and positive pi over 2. Those are the only two places between, these two numbers are the only two places between negative pi over 2 and 5 pi over 6. So I'm going to take my critical numbers, and in this case, my critical numbers, I have 3. I have the 2 endpoints of my domain, and then one value that is in between them. My critical numbers are theta equals negative pi over 2, pi over 2, and 5 pi over 6. And I'm going to take them and test them in my original function. So we started with f of theta is sine theta. I want to know where the absolute max and the absolute min occur for this function. So negative pi over 2 came from an endpoint. Pi over 2 was a critical number where we solved the derivative equal to 0. And 5 pi over 6 is the other endpoint of my domain. So when I plug those values in, sine of negative pi over 2 is negative 1. Sine of positive pi over 2 is positive 1. And sine of 5 pi over 6 is 1/2. So when you look at these three output y values, the function output values that I have here, you notice we have the smallest number is negative 1. That's my min. And the largest number, positive 1, is my max. So what we can say is the absolute max on this interval, the absolute max is 1, and it occurs at theta equals pi over 2. And the absolute min is negative 1, and that occurs at theta equals negative pi over 2. So if we consider this graph of sine theta, and we know what the graph of sine theta looks like, right? Sine theta looks like this, continues in this direction. So if we think about it from negative pi over 2, which is going to be at that peak as it curves around over there, and 5 pi over 6, So 5 pi over 6 is a little bit bigger than pi over 2. Here's my graph going to pi. I'm going to erase a little bit of it because we don't need all of that there. So just to pi, but what we care about is the right endpoint, which is at 5 pi over 6. And 5 pi over 6 is right about here. So really, the graph that we are looking at is between here and here. And you can see where the absolute lowest point on this graph is. The absolute min is at negative pi over 2. And the absolute max occurs somewhere on the interior of the graph, right here, at positive pi over 2. So we've got negative pi over 2 is the min, positive pi over 2 represents the max. And the other endpoint of my domain here, 5 pi over 6, is a relative min, but it's not an absolute min or absolute max. Okay? So absolute max, absolute min, you just need to remember to check the endpoints of the domain, the derivative equal to 0, and then any undefined values for the derivative or the original function, which we would have left out in the domain.